Good morning, everyone. Let's get started. So in the previous classes, we looked at a number of results which dealt with typical sets. We defined the notion of a typical set, a jointly typical set, and we saw some of the properties, both formal mathematical properties as well as the sort of intuitive or geometric properties of typical sets and what they look like for the specific case of the binary symmetric channel and basically for binary sources. Right. And so in this class, we'll use the tools that we've studied in order to prove the achievability part of the channel coding theorem. So we'll first see what encoders are, what kind of decoders you can construct, what is the difference between different encoders and decoders that you can use, and to distinguish between what is used in practice, the kind of decoders which are used in practice, versus the kind of decoders that we use to prove achievability theorems in information theory. So although I will give a proof of the channel coding theorem, which tells you that there exist codes approaching rates close to capacity and probabilities of error approaching zero, it does not really tell us how to construct practical encoders and decoders. And that is why it was only in the recent couple of decades that we were able to actually construct good codes which get you at rates close to capacity. All right. So before we proceed, any questions from the previous classes? All right. So let's look at the formal problem setup. Let's do a quick recap. So the goal is to transmit a message across a discrete memoryless channel. The discrete memoryless channel is specified by three things. An input alphabet, which tells you what kind of symbols can be sent across the discrete memoryless channel. An output alphabet, which tells you what kind of symbols are received by the receiver, and the relationship between x and y. So that is py given x, which is the transition probability. So given that you transmit a symbol x, if you send a symbol x through the DMC, then you receive some other symbol y through the DMC with probability py given x of y given x. All right. So for example, although it's not over the discrete alphabet, but for an AWGN channel, the probability of receiving a particular real number y, given that you sent some other real number x, is given by the or the density is given by the density of a Gaussian. Right? So y is distributed according to a Gaussian with mean x and variance some sigma square. Right. And similarly, we also have seen a number of channels, including the binary symmetric channel and the binary erasure channel. Okay. So this is a description of the medium or the channel across which we are transmitting, and our goal is to transmit a message W across this channel. And to do so, we want to transmit kn information bits. So we'll assume that the message is uniformly distributed over 0, 1 to the kn. So basically you have kn IID Bernoulli half random bits, and you want to send this across the channel, and we want to design some kind of a scheme so that this is so that the receiver can estimate this with a vanishingly small probability of error. Right, and to do so, we won't transmit W directly across the channel. We will encode it using an encoder, which I denote ENC. So the encoder takes as input kn message bits and outputs a sequence of length n, which we call the code word. Right, so this n-length code word is what is actually transmitted across the discrete memoryless channel. Each component or each entry of the code word is independently corrupted to give a received vector. We'll call it yn. And the decoder is going to be another function which takes as input the received vector and outputs an estimate of what was actually transmitted. Right? And our goal is to construct these encoders and decoders such that the probability of error is vanishingly small. So we want the probability of w hat not equal to w. So we'll call this PE to be vanishingly small. So it's little o of 1. And at the same time, we want the asymptotic rate, which is the lim sup as n tends to infinity of kn by n. This should be as large as possible. And our interest is in knowing what is the maximum r at which we can transmit, such that the probability of error, such that we can construct encoders and decoders for which the probability of error is vanishing in n. And we've already seen that this is given by, according to Shannon's channel coding theorem, we can make R to be arbitrarily close to the capacity, which is the maximum mutual information between X and Y. Okay, so our goal in this class is to understand the concepts of the channel coding theorem, and some of these concepts are very important and sometimes not very intuitive. So although we have discussed the proof of the channel coding theorem in previous courses, we will revisit this in some amount of detail, because there are certain concepts which are not obvious or not very intuitive. So as I mentioned, for any channel coding scheme, there are two main objects. One is an encoder and the other is a decoder. And we'll explore this one at a time. Right? So first, what is the code? Right? There's one thing, which is the encoder, which maps messages to code words, and the decoder maps received sequences to estimates of the message. All right. So let us look at the code. All right. So the code or the code book is the set of all possible code words which can be transmitted. So it's a set of all code words. All right. So if so I have messages 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1. So all possible kn length messages. All right. So how many possible messages can there be? So how many, since we're transmitting kn information bits, how many possible messages are there?
Depends on number of bits.
Correct. So there are kn bits, right?
2 raised to power kn.
2 power kn.
Right. So there are 2 power kn bits. So this is message number 1. This is message number 2. Similarly, there are 2 power k subscript n number of messages. And corresponding to each of these, so if I want to transmit, so if the actual message is message 1, then I'll transmit some code word. Let me call it xn of 1. If the actual message is message 2, maybe I'll transmit the code word xn of 2, and so on. Right? If it's 2 to the kn, if actually it's the 2 to the knth message, then I'll transmit xn of kn. Sorry, 2 to the kn. right? And this entire collection of possible code words is what I call the code book, and they denote it as whatever calligraphic C. Right? This is my code book. So all the possible uh, code word sequences that might be transmitted. All right. So given a code book, let us see how we can construct a decoder. Right. So these are possible code books, and the received sequence can lie anywhere in yn. Right. So you receive yn, which is any possible sequence. So for example, for the BSC, the received sequence is any binary vector. For a BEC, this could be any vector containing zeros, ones, and erasures. All right, and we want to design a map. So basically, this is what would happen. You have a bunch of messages. All right, these are messages. This is maybe the set of all possible transmitted sequence xn. So each message gets mapped to one particular code word. Right, so this is what the encoder does. The encoder maps every sequence to some particular code word sequence. There could be some sequences in xn which are not valid code words. Right, and corresponding to each of these, you transmit xn through the channel, and you receive a sequence yn. So this could be a bunch of points. So yn consists of a bunch of points, and the decoder maps each sequence to a particular message. So multiple received sequences could be mapped to the same message. Right? And really the art is to design these encoders and decoders satisfying various constraints. Okay. Now there are different decoders that one can use, and all of these depends on what your criteria are. So the first criteria is, of course, suppose I don't care about computational complexity. Not that there are many aspects that one needs to keep in mind when designing these encoders and decoders. The first is, of course, you want the probability of error to be as small as possible, which will be our main concern in this course. But in addition, there are also practical requirements, and the most practical requirement that you can think of is that the computation involved but must not be too large. So both encoding and decoding must be done as fast as possible. It should not take too much computational overhead. That is, it should not involve too many arithmetic or Boolean operations. And at the same time, it should not take too much space. So if there's something that you need to store in memory, maybe the set of all possible code words, then this should not take too much space. So there is, of course, you want to make sure that the probability of error is small, but also keep in mind the complexity, both in particular the computational complexity. So computational complexity should also be very small. Right? So this was the probability of error and the rate, and of course the space and time complexity of the encoding and decoding processes. Now, for now, if we ignore the computational complexity aspect of it, the best decoder, so given a particular code book, so suppose that you fix a particular code book, we want to know what kind of decoders we can construct. Now, in general, the optimal decoder for any channel coding problem will be the so-called map decoder, or the maximum a posteriori probability decoder, the map decoder. All right, and the map decoder in particular, so this is a decoder that you will see, that you would have already seen in a digital communications course. So the map decoder does the following. So given a particular code book, so suppose that you have fixed a code book, then the map decoder works in the following way. The map decoder computes the estimated, say, W hat to be the argmax over all possible messages W in 1, 2, up to 2 to the kn of P of xn given yn of xn of W given yn. So given a particular received sequence, the map decoder outputs that particular code word which is most likely to have been transmitted. All right. So given a particular yn, you output that xn of W, that code word, which maximizes the probability of xn given yn. Right? And one can formally show that for any problem, the map decoder always minimizes the probability of error. So for a fixed code book, the optimal decoder is always a map decoder. So this is one particular decoder. The second is what is called the maximum likelihood decoder. All right, and the maximum likelihood decoder is similar to the map decoder. It maximizes what is called the likelihood function W in 1 up to 2 to the kn of Pyn given xn. So given a received sequence yn, you try to find the code word which maximizes the probability of having seen the received sequence. All right, and it turns out that ML decoding is equivalent to map decoding if all the code words are equally likely to have occurred. All right. If not, the maximum likelihood decoder is in general different from the map decoder. So the map decoder always minimizes the probability of error. The ML decoder is equivalent to map if the inputs are equally likely. Okay, so in many cases, one generally looks at the ML decoder because sometimes it's easier to analyze that. Computing the map, so computing this, so you can always obtain this from this using Bayes' theorem. Right, you just use Bayes' theorem to go from Pyn given xn to Pxn given yn. But in many cases, it is more practical or it's slightly more convenient to look at Pyn given xn instead, and that is why in general you look at the ML decoder. And the ML decoder also has some other nice properties, but I don't want to get into too much detail. So if you've taken a course on estimation theory, you will have seen that the maximum likelihood estimator has certain nice properties in that, certain nice asymptotic properties. But that's if you haven't seen it before, it's not important. So these are two of the sort of best decoders that one can come up with, but there are multiple disadvantages. One, it is computationally very hard to compute the map estimate or the maximum likelihood decoder, and also it is not very intuitive. The geometric properties are a little harder to analyze in general. Even if you want to prove any sort of theoretical results, it is very hard to do so using the ML or the map decoder. So we generally go for other non-map and non-ML decoders because either A, they have lesser computational complexity, or B, they are more convenient to prove various theorems. All right. So before we proceed, are there any questions so far? Okay. So these are two decoders which are used or which are analyzed in practice. The third, something that we will extensively use, is the typical set decoder or the joint typicality decoder. All right. The joint typicality decoder does the following. So given that you see a particular yn, so suppose that you receive yn, you estimate that x. So w hat is equal to, so it's equal to some particular w if that the code word corresponding to w and yn, these are jointly typical for some particular fixed parameter epsilon. All right, so if there is one code word which is jointly typical with respect to the received sequence, then you output that. And at the same time, there should be no other code word xn of some w prime. If you look at any other w prime, xn of w prime yn. So if you pick any other w prime and look at the corresponding code word, then this does not lie in the typical set. So there is only one code word which is jointly typical with respect to the received sequence. All right, and suppose that you do not see anything. So suppose that you cannot find a code word which is jointly typical with respect to yn, or if there are more than one code, if there's more than one code word which is jointly typical with respect to yn, then you output either you output an error, you say sorry I cannot decode, or you just output something random. Okay. So this is what joint typicality decoder does. Any questions? Okay. So so there are other related decoders, but only for very specific channels. So for certain channels, such as, yes.
if x and w is typical with more than one yn, then what happens then? Like if
No, you receive a yn, right? The goal is having seen one particular yn, you want to output some w.
So now, we just choose that code word that is jointly typical with yn, right?
Correct.
So now, what happens if more than one x in of w is jointly typical with yn?
Correct. So if more than one code word, not input sequence, remember?
Yeah.
So
code word.
so xn of w, so it's a strict subset of all the possible input sequences. And if there is more than one code word which is jointly typical with respect to the received sequence, then you just output some random message. Maybe always output message 1. If you're not sure, then you output message 1. Or in other words, it is the all zeros sequence, since we're looking at the message as a sequence of bits. Okay. So this is so these are 3 decoders, but for specific channels such as for example, the binary symmetric channel or the AWGN channel, we can decode in terms of distances. So the input and output space have some kind. These are metric spaces. So there is a notion of distance between points. In general, for arbitrary input and output alphabets, there's no notion of distance. But whenever you have a notion of distance, you can define what is called a minimum distance decoder. Right? And the minimum distance decoder basically does the following. It outputs an estimate, which is the code word which corresponds to the code word which is closest to the received sequence. So if there's some distance, so if we define some distance between points in the xn and yn space, we'll assume that xn is equal to yn, and this is equipped with some particular distance. Okay, for such cases, we can define the a minimum distance decoder in the following manner. So it is the xhead of w, which is closest to the received sequence yn. Okay, so this is the so-called minimum distance decoder, and what you can show is for the BSC and for the AWGN channel, the minimum distance decoding is the same as ML decoding. Okay, so I encourage you to do this. So as a homework, show that at least for the BSC, prove this particular statement, that the minimum distance decoder is the same as the ML decoder, and you can prove this very simply. Just find what is PYN given xn, express it in terms of the minimum Hamming distance between xn and yn, and show that maximizing the likelihood function is the same as minimizing the Hamming distance between the transmitted and the received sequence. All right. So this is the minimum distance decoder, and another similar notion is what is called the bounded distance decoder. So this is somewhere in between the minimum distance decoder and the typical set decoder. So the estimate is equal to W. So the bounded distance decoder again applies to to these cases where xn equal to yn, and there is some notion of a distance between points. And in addition, you have some parameter rho, which is sort of the bound on the distance. So this is called the decoding radius. So the output, the estimate is equal to W if the distance between the Wth code word and yn is less than or equal to rho, and there is no other code word within distance rho of yn. So for every other W prime, the distance so for every other W prime, the distance between xn of W prime and yn is strictly greater than rho. Okay, and if not, then you either say you cannot decode or you always output the all zero sequence. All right. So let's look at this geometrically. Let us take the example of, say, the AWGN channel or the BSC. So again, this will be purely some geometric interpretation. Yeah. So suppose that this is the code book. So code book is nothing but a set of code words. So it's just a bunch of points in xn space. So we'll assume, at least for this example, we will assume that xn equal to yn. So these blue points correspond to the various code words. All right. So at least for the BSC and the AWGN channel, minimum distance decoding is the same as ML decoding, right? And what the minimum distance decoder does is that it basically partitions the space into regions. So you have a partition into regions where each these points are partitioned depending on which is the closest code word to them. So maybe this is what the partition would look like. Right. So basically you have xn, and then you partition it into a set of all points which are closest to the corresponding code word. So any point in this region is the closest code word is this one. So for every point in this region, the closest code word is this one. For every point in this region, the closest code word is this one. So this is, at least when you're talking about Euclidean spaces, this is sometimes called the Voronoi partition of space. All right. So what the ML decoder does is that, so let us say that you receive some particular sequence. Let us say that you receive a point over here. Then the estimate is basically the message corresponding to this code word. If the received sequence is here, then the estimated message is the one which corresponds to this code word, and so on. Right. So that is what the ML decoder or the minimum distance decoder would do. Note that the ML decoder is not the same as minimum distance decoder for all channels. It's only the case for the BSC and the AWGN channel. In general, you could always, so for example, if you had a binary asymmetric channel, then minimum distance decoding is not the same as ML decoding, but you can still define both the ML decoder and the minimum distance decoder. Okay, so this is what the minimum distance decoder would do. Now, what would a bounded distance decoder do? So the bounded distance decoder would basically do the following. So you define basically a decoding radius. All right, let me put this in orange. So for each code word, you draw a ball of radius rho around each code word. Right. So this corresponds to bounded distance decoding. Right, so this radius is 0. So given any received sequence, you look at, you draw a ball of radius rho around the received sequence. So let us say that you actually received this particular sequence over here. You draw a ball of radius rho around it and see if there is a unique code word in this particular region. If there is no code word, then you just output 1, right? But let us say that you received a sequence somewhere over here, right? If you draw a ball of radius rho, then you'll see that there is a code word, which is this particular point, within a distance of rho to it. And there is no other code word within distance rho. So in that case, you output this as the transmitted code word. So basically, if the received sequence lies in any one of these orange balls, in exactly one of these orange balls, then the output is basically the center of that particular ball. Right? So if you receive a sequence over here, it is the decoded code word is this. If you receive a sequence over here, then the decoded code word is this. If you receive a sequence over here, then the decoded code word is this one. But let us say that it lies outside any of these balls, then there is no code word within that particular distance, and basically it corresponds to an error. All right. And similarly, if it lies in the intersection of two balls, so maybe it lies over here, then there are two code words within a distance of rho to this particular received sequence. So you'll say you just basically give up on decoding, you'll just output the all zero sequence. Okay. So that is basically bounded distance decoding. All right. And note that minimum distance decoding is not the same as bounded distance decoding. Even though the bounded distance decoder fails, for example, when the received sequence is over here, the ML decoder will always output a unique code word, right? So the ML decoder would have outputted this particular code word, whereas the bounded distance decoder just gives up. So the bounded distance decoder always has a higher probability of error than the minimum distance decoder. All right, but we still sometimes analyze the bounded distance decoder because it is either it's computationally sometimes a little more efficient than minimum distance decoder, or there are some nice geometric properties that you can use and you can analyze the bounded distance decoder more easily. All right. Any questions so far?
Sir, how to know what is the, like how we can decide upon the decoding radius?
Oh, the decoding radius. That's a good question. So it's not always easy to decide what the decoding radius should be. But in general, so generally what you do for very large n, for for large n, the decoding radius is generally chosen to be close to the radius of the noise ball. So what do I mean by this? So let us say we have, say, the BSC, say BSCP. Then it's easy to show that if you generate Bernoulli P random variables just by Chernoff bound, you know that the Hamming weight of the noise or the Hamming radius of the noise ball is going to be roughly close to NP. So you take the decoding radius to be very close to n times p. So similarly, if it's an AWGN channel, then if it's an AWGN channel with variance sigma square, then you take the radius of the noise, then you take the decoding radius to be the radius of the noise ball, which will be close to square root of n sigma square. But in general, for other problems, it may not be very easy.
Sir, one more question.
Yes.
What are maybe the decoding radius? Will that vary for each and every partition, or will that be same?
So again, for the same code, you could define different bounded distance decoders, right? So you could just change the decoding radius. If you kept the decoding radius too small, so note that for any bounded distance decoder, there are two kinds of errors that may happen, right? So either the received sequence. So if you look at the bounded distance decoder, there are two sources of errors. One, there is no code word within distance of rho to the received sequence, or there is more than one code word within distance rho. Right? So if the decoding radius, if rho is very small, if the decoding radius is very small, then so basically this will happen. The second type of error will happen if there is a lot of overlap between balls, right? So in this case, you will have a lot of so if rho is very small, then most of these balls will not overlap. So there will be very few type 2 errors. But if the radius is too small, then it is very likely that the received sequence will lie outside the other balls. There'll be a lot of space vacant in between. All right. So the type 1 error will be large. So type 2 error will be small, but type 1 error will be large. Similarly, if rho is large, then the number of type 1 errors will be small because most of this empty space will be filled up by at least one of these balls. But if the radius is too large, then the type 2 errors will go up, right? Because there'll be a lot of many balls which will intersect with each other. So it's really sort of so you have to strike a fine balance between the type 1 and the type 2 errors. So you can't keep the decoding radius too small. At the same time, you cannot keep the decoding radius too large. All right, and in fact, for let's say the BSC or the AWGN channel, the right balance between the type 1 and the type 2 is achieved when you choose rho close to NP or square root n sigma square, and you choose the number of code words to be roughly close to 2 raised to n times the capacity. Any other questions?
Sir, one
Yes.
more. Sir, let's suppose if those sir boundaries, if they overlap each other.
Two balls, you mean?
Yeah.
Okay,
Two
so something
circles, sir,
like
if
this.
they
Yeah.
overlap each other, sir.
Okay.
Then let's suppose there is a particular code word, or let's suppose there is a particular message which falls in between that particular overlapped region.
Correct. So let us say there is so you actually transmitted this code word, but then you received something over here.
Yeah.
Right?
So
That's it.
even then, sir, the chance of having a misinterpreted message, or you can have that the chances will be more, even if they have a overlap thing, right, sir?
Correct. So in general, this will be an error because you don't know, at least the bounded distance decoder will make an error because it just gives up. It says, I don't know how to decode this, right? But on the other hand, if you use the minimum distance decoder, then you could still be able to decode it correctly.
So, sir, is that possible to have a combination of both bounded distance and minimal distance?
So I mean, you can come up with any decoder you want, but by definition, this is what a bounded distance decoder would do. Right. So in practice, what you use, for example, in let's say the kind of codes that you use in the 3G, 4G, or 5G standards, they neither do minimum distance decoding nor do they do bounded distance decoding. They do something completely different, which are computationally very efficient, and and those I guess, yeah, so it would be somewhere in between the two, and maybe not even in between the two, because you can the kind of errors that they can make could look, the geometry of the kind of errors that they make could be very, very different. Right? But these are sort of common decoders that one can use because they are because they're either convenient to analyze or, of course, the ML decoder because it is optimal in some sense. But in practice, you rarely ever use ML decoding unless they're for very, very short block lengths and you want a very small probability of error. But for in general, for data transmission, you never do ML decoding, or at least you never do block-wise ML decoding.
Sir, a small question.
Yes.
So if we increase the radius, there will be maximum like overlapping possibilities, and
Correct.
if we decrease it, there will be more region where there won't be any, I mean,
Correct.
empty spaces as
Correct.
well.
Correct.
So how can we achieve the balance, sir? Like, is it possible?
So that's what I said, right? So the sort of, at least for the BSC or the AWGN channel, the sort of balance is achieved when the number of points, the number of code words is close to 2 raised to n times the capacity, and uh, and the decoding radius is chosen close to n times p or square root n sigma square.
But this is just to decrease the probability of error, right, sir?
Correct, correct, correct. Oh, you're speaking purely in terms of a geometric problem?
Yes, sir.
Okay, so that is a little harder to sort of study, and it's a little harder to define as well. So there are different problems that you can look at. So this is the so-called. I mean, there are two things, right? So one is you want to minimize the overlap between balls, and the other is you want to cover as much of space as possible. So one thing is to minimize overlap, and the other thing is to minimize the amount of empty space. Right? And these two are in fact complementary problems. So there is a so-called covering problem, which basically asks for the minimum number of points which covers the entire space. There is no space left in between at all. And the second is the so-called packing problem, which asks for the minimum number of points that you can use, such that you can pack in balls such that no two balls overlap. And in fact, these are two different problems. And what we want in the context of channel coding for random, so for DMCs is something in between. We neither want to really cover all of space, but at the same time, we don't want to achieve a hard packing. We're okay if there is a small amount of overlap in between, but the overlap should not be too large. And in some sense, it is okay to leave space in between. So remember that our goal in the channel coding problem is to only minimize the probability of error. Right? So in that case, neither of these are particularly a hard requirement, but basically what we achieve is sort of a balance between the two. I'm not sure if that answered your question.
Yes, I get it. Understood.
Yeah. So if you look at classical error correcting code, so for example, if you're also simultaneously taking the error correcting codes course, or you've done it before, the flavor of problems that you study is closer to that of packing. You want to basically construct codes which have a large minimum distance, and that effectively corresponds to the packing problem. But then if you want to use these codes to transmit over, let's say, a BSC, then these are not optimal because they don't get you close to the capacity. The rates that you can achieve are way below the capacity. So in fact, for DMCs, we do want to allow for a small amount of overlap between these balls, right? And that really gives us that extra room in order to achieve the best rate. All right. Okay. So this is what happens for bounded distance or minimum distance decoding. Typical set decoding is something a little more different. So in fact, what a typical set decoder would do, although it's not an accurate description, but roughly speaking, what a typical set decoder would do is say that the sequence is typical if or the received sequence is decoded to one particular code word if it is jointly typical with respect to one particular code word. Right? So corresponding to each of the received sequences, you have the set of sequences which are typical with the set of code words which are typical with respect to the received sequence. So recall that the typical set, so for a given code, so for a given transmitted code word, the set of sequences which would be typical with respect to this code word would be sort of lying in a shell, right? So they would lie in some particular shell. So if the received sequence lies in this particular, if the received sequence lies in this particular shell, then it is decoded to this particular code word. If it lies in this particular shell, it is decoded to this code word. If it is overlapping, so if two shells overlap, then it is jointly typical with respect to both this code word and this code word. And the decoder basically just gives up. It says, I don't know how to decode. I just output something random. All right. So this is sort of the geometrical difference. So minimum distance decoder would partition the space into non-overlapping regions such that each point is uniquely closest to one particular code word. Bounded distance decoding, you basically, for the received sequence, you look at the distance to each possible code word. If there is if there is exactly one code word within distance row, then you say that, okay, this is the received code, this is the transmitted code word. Whereas a typical set decoder would say, okay, if there is exactly one code word which is jointly typical with respect to what I have seen, then I output that. If not, I give up. Right? So similarly, so basically for the BSC, if the received sequence lies in this particular shell, in exactly one particular shell, then you output the code word corresponding to that shell. If it lies outside any of these shells, or if it lies in the intersection of two shells, then you say, okay, I don't know what to do. So in fact, even if the received code word is very close to the transmitted code word, right? It's possible that the decoder could make an error if you use typical set decoding. Because in this case, you would say that this is not jointly typical with respect to this particular code word because it does not lie within this particular shell. All right, so in general, the minimum distance decoder, at least for the BSC, the minimum distance decoder would give you the best performance. The bounded distance decoder would give a slightly worse performance in terms of the probability of error. And the typical set decoder would give the worst performance out of these three. And in fact, to prove the channel coding theorem, we will prove that even if you use a typical set decoder, you can still achieve a vanishingly small probability of error. Right? So obviously, if you can do well using the typical set decoder, then you can obviously get a lower probability of error if you used a minimum distance decoder, right? Or a map or an ML decoder. All right. Any questions? Right. So now we've had an extensive discussion regarding the kinds of decoders that you can employ, the kinds of decoders which are optimal versus the kinds of decoders that we can easily study in practice. And in the next class, we'll actually analyze the probability of error for a typical set decoder. But now the question is, how do you choose the encoder? How do you choose the codebook itself? All right. So one brute force approach is, so basically what do we need? For each message, all right, for each message, you need to identify a particular code word. So the encoder, in one way, if you don't care about computational complexity, you can maintain a table, right? A table of W versus xn of W. So maybe the all zero sequence is encoded to some A, B, A, B, if this is your alphabet. And similarly, this could be B, 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 whatever, right? So you maintain a table. So for this message, you transmit this code word. If it is this message, then you transmit this code word. If it is this message, then you transmit this code word. Right? So that's one way of encoding. But the question is, now, how do you choose the codebook itself? How do you choose this sequence of code words? Because some code words could be very bad, some code words could be very good. And it's not easy to choose the right codebook because the space over which you want to find, the space of all codebooks is really, really huge. Right? It's actually doubly exponential in n. So the optimal way to do it, if you wanted to choose the best possible code, would be, okay, let us say, so I'll pick a particular decoder. So for a given codebook, I will fix a decoder, let us say the minimum distance decoder or the typical set decoder. Okay, I'll fix a particular decoder. I want to find the best possible code which minimizes the probability of error. So you fix the decoder, you fix Kn, and now you look at all possible codes and try to find the best possible code. So your code book is the minimum over all possible code words, all possible code books with 2 to the Kn code words is equal to 2 to the Kn, and which minimizes the probability of error corresponding to this particular decoder. Right? So you look at all possible ways of filling this table, and then out of those, so for each table or each set of code words, you calculate the probability of error, and then you choose that code book which minimizes this particular probability. Right? So that's a completely brute force approach. For a discrete memoryless channel, in principle, it is possible. Right? Theoretically, it is possible to do this, but solving this optimization problem practically is impossible. Right? Because the number of ways of filling this table is huge. Right? So this would give you the best code, but it's not possible to find the best code, and it's not even possible to analyze what is the probability of error for the best code. So what we do, and really that was Shannon's biggest contribution, which really sort of introduced information theory, or the main power behind information theory, was that instead of looking at the best code, you look at an average code. So let us say that I fill these entries of this table randomly. So each entry I choose IID according to some distribution. So I choose each code word at random, and then I find out what is the average probability of error if I choose a random code. I just fill this randomly, and for a random code, I try to analyze the probability of error. That turns out to be easier to do. And for that, if I can show that the average probability of error is vanishing in n, it means that the minimum overall possible code books of the probability of error, that should also be vanishing in n, because this can only be better. All right. So instead of looking at the minimum overall possible code books of the probability of error, you look at the expected probability of error for a random code. Okay, and in fact that is the main tool used to prove all achievability results in information theory. Right, and just because the average is going to be at most, the minimum is obviously going to be less than or equal to the average. It's enough if we show that the average probability of error is small, then it means that the minimum overall possible code books of the probability of error will also be small. So there exists at least one code which achieves a vanishingly small probability of error at a particular rate. Right? So neither of these tells us exactly how to construct the code, right? Or it doesn't tell us how to construct the code efficiently. But it does tell us that it is possible to construct a code. That gives us some hope, and then we use completely different tools in order to design efficient codes which perform well over discrete memoryless channels. All right. Any questions? So this conceptual understanding of what it means by a random code and why you choose a random code, this is particularly important, and how do you decode. So remember that behind all of this is the following principle. You fix a particular decoder, which works for any code book, say the minimum distance decoder, or the ML decoder, or the typical set decoder, and then you look at the best possible code which minimizes the probability of error. You can't really study that, so instead you study with respect to a random code, okay, and find on average. So you look at all possible codes, and if you average it out over all possible codes, then what is the probability of error? If that is small, then it means that there is at least one code for which the probability of error is small. And that basic idea is the heart of all achievability results in information theory. So this is sometimes called, this broad idea is called the probabilistic method. And this is one such tool among the set of all probabilistic methods which are used to prove these results. So you don't explicitly demonstrate a particular code. I don't give you one particular code. It's an approach to look at all possible codes and see and show that out of all possible codes, there's at least one code which is good. All right. Any questions? Okay, so if not, we'll meet in the next class. So in the next class, we'll see how to construct the random code, and then we'll analyze the probability of error of a typical set decoder for any general discrete memory list. Okay, so see you all in the next class.